Okay, welcome to the third part of today, where we continue our theories of problem solving. Okay, so we spoke about behaviorism, Gestalt Psychology, and the Representational Change Theory, and now we will speak about the information processing approach and very briefly about analogical problem solving. Okay, so information processing approach. And this was founded on the observation that in our everyday life, most problems that we do encounter don't have this element of insight. So when we have a problem in our everyday life, it's not like that we sit down into a quiet corner and then suddenly say, I have the solution. But instead, it's just we try to find different solutions. So the example would be we may have a date or an appointment and our car does not start. And we may try to fix it ourselves, or we may call a friend to drive us or something, or use public transport. So we have already different solutions available. We just consider them, which ones are most appropriate for the current situation. And then we pick that one. But we don't have this I don't know what I want to do, I don't know what to do, and sit down and then I could call a friend. And that is suddenly. Sometimes it is involved, but generally it's not really the main characteristics. And Simon and Newell asked, mouse acting up. Simon and Newell asked, for these type of problems, what strategies do we use to solve them? And they put that into quite a formal description. They said it is actually a search through a problem space. So what is such a problem space? It's basically all possible states or solutions in a problem. And this can actually be very, very large. And we will see an example in a moment. It's best described for very well-defined problems. And the problem space offers an objective measure of optimal solutions, because usually we have like a start point and a goal end point, and we can see how many moves do we need to make through this problem space. How many moves do we need to solve the problem? And the solution with the least moves is usually the optimal solution. So, like we already had in the introduction, we have an initial state, the starting point. And this gives us information about where we are. And we have the goal state, the desired end state or solution. And we have operators, which are the set of permissible operations that can be performed. So things we can do. And if you think, for instance, about a race you want to do and you want to win that race, then, for instance, it's not permissible to take shortcuts. An example which is very, very frequently used for these type of problems is the Tower of Hanoi or Tower of London task. And you probably know that very well. You have the start state where you have these disks with different sizes on one peg, and your goal state is to bring them over to another peg. However, to do that, you have a couple of rules or operators. And one is that you are allowed to move only one disk at a time from one peg to another, and that you can only move a disk which is on top, so it's not allowed to have another disk on top of it, and you can't put a larger disk onto a smaller disk. It must always be this shape, smaller on larger. So for a simple 2-disk version, this would be the problem space for that. These are all conceivable moves and constellations we may have. So when this is the start state, we could take the small disk and put it on this peg, or we can put it on that peg. We only have these two options. When we are here, then the only sensible move would be to put the large disk here, but because when we put the small disk here, we have actually this state here. So we may put the large disk here, and then we could put the small disk here, and we could go back and forth between them. And then we could put the small disk on top of this, and we could go back, and here we have the path for putting them on the third peg and here on the second peg. So you see, this problem space describes all possible combinations, all possible states of the problem, and you may track what a participant is doing when they want to solve that, and they may do something like going here, getting confused, going back, going here again, going back and forth, and maybe need 12 steps or something, although the fastest solution would be 1, 2, 3 steps. I don't need more, no matter where I want to put that. I can do it in 1, 2, 3 steps. This is a very simple problem, the 2-disk version. When you have the 3 or 4-disk version, this problem space is basically exploding. You have so many different variations of how you could arrange the disks that it got just tremendously huge. Just for a little entertainment, here's a little video of people trying to do that as a competition as quickly as possible. You see they start here, and I think this person tries to get all pegs over to this one, all disks over to this one, and this person over to this one. And they are obviously well trained, and see how quick they work their way through that.
Whenever you're ready.
There you go.
Once you understood the principle of this task, it's actually quite easy to do because it's always the same strategy of how you have to move the disks around to make one free, and then you can move it over and then you put them all back. And it doesn't matter at some point how many you have, it just gets more tedious in the end. First one is finished, and we can just stop it here. Okay, so let's have a look at this problem space again. As we said, it contains all possible states in a problem, and so can be very, very large. However, as we have learned in previous lectures, our short-term memory or working memory is rather limited, and this is the place, our working memory, where the problem space has to be kept online to search through it in our mind. So it's not a long-term memory structure which would have unlimited storage, but it's actually a short-term memory structure. So that's a problem, and it's actually often impossible to generate and hold the entire problem space in mind and then search through it for the optimal solution. It works well if you want to simulate that in computers, but even with computers, you may reach the limit of available processing power, and if you're interested in that, you can search for the problem of the traveling salesman, where the problem space becomes so big that even current computers have troubles finding a solution in a manageable time. So if we can't do that in our mind for more complex problems, how can we find a solution then? The answer is that we use heuristics. And I would like to introduce just one heuristic just to illustrate the principle of what a heuristic is. And the idea is that we use a strategy which is much less demanding than a proper search through the problem space, but which still often produces a solution, a satisfactory solution. It doesn't need to be the optimal. It's often sufficient if it's a good one. If it's one which works, even if it's not the optimal. You may also say a heuristic is a little bit like a rule of thumb. And as an example, we already have seen trial and error, which is kind of a heuristic. And another example would be the so-called hill climbing heuristic. And to follow these heuristics, we don't need to require a real understanding of the problem. For some heuristics, we may need a partial understanding, but not in total. So what does the hill climbing heuristic say? It's a very simple and straightforward one, which says that if in doubt, choose a move which brings you closer to your goal. As simple as that. So if you can't think of anything else. So instead of going further away. So if your goal is to reach the peak of a mountain, then walk uphill, not downhill. And this often results in a fair solution. However, you probably in this image can quite easily see the problems with these type of heuristics. And that is, sometimes you need to make a move which leads you further away from the final goal to really solve the problem. So in this example, if you want to reach the highest peak, marked in red here, on your way you may need to go a little bit downhill as well for a brief amount of time and then uphill again. So if you follow the hill climbing heuristic very strictly, then you may not reach the highest peak, which would be the optimal solution. However, it still would bring you to this second highest peak. So this might be totally acceptable. You have a beautiful view. You will not land down here somewhere in the valley or something. So such a heuristic can be sufficient. Okay, to summarize, the information processing approach works well for well-defined problems. And the definition of a problem space allows for very objective measure of performance and the different solutions and things like that. And this information processing approach actually resulted in the programming of quite successful computer models, such as the General Problem Solver, GPS. It has limitations of the nature that a lot of everyday problems are ill-defined and that it does not perform very well on these insight problems, although they may be rarer than the other ones, but they still exist and it doesn't offer the best solution for them. Okay, let's turn to the last theory, and this is analogical problem solving, and I just want to touch upon this very briefly to introduce the basic concept or idea, what's behind that. Okay, I would like to start with an example. Suppose there is a village with 20 male and 20 female singles. A matchmaker manages to set up all into 20 couples. However, the night before the weddings, 2 men get cold feet and run off. Will the matchmaker be able to rearrange the remaining singles into 19 couples? You can think about this for a short moment and pause the video. Okay, so will it be possible? No, it won't be, unless there are gay couples, which we just rule out for the example of that. Okay, maybe you have noticed that. If not, think about whether this problem has a similarity to anything which we have discussed already today. So today means not only in this video, but maybe the other parts of this lecture on problem solving and expertise as well. It's basically the same underlying structure with like the mutilated checkerboard problem. Because in the mutilated checkerboard, when you place a domino on a black and white pair of fields on the checkerboard, this is like making a match. And in the checkerboard, we removed 2 white or 2 black squares, and by that create the same situation like here, that we suddenly have more white than black or the other way around, and here we have more women than men. And here it is rather evident, because when we think about couples, we more directly think about, matchmaking. It should a man go with a woman. In these type of standard, these tasks are a little bit old. I don't want to imply anything here. It's just for illustration, taken from textbooks and stuff. In the other one. And analogical problem solving means that if we have spoken about the checkerboard problem, that you find that one easier, because you make the analogy and say, well, I heard the same thing before, I can apply that to this problem, and so it will help me solve that problem. And I don't know about you, but in this order, it's a little bit more challenging to see that this is actually the same as a checkerboard. I mean, this one is a little bit easier anyway. A good research question would be when you read that one first and then you get the mutilated checkerboard, which a lot of people find very difficult, whether then the likelihood to solve the mutilated checkerboard problem would increase. What research has shown is that this is very difficult, actually. So to recap quickly, analogical problem solving means we should learn something by solving a problem, so that we are able to solve the same problem again, or that we can transfer the solution to solve similar problems. And this is called analogical problem solving. But as I already alluded to, making these analogies is actually very hard. And a lot of studies have shown that if you try that, you give them one problem and then they do some random task in between and you give them another problem, and these two problems are connected, that if it's not totally obvious how they are connected, people make very little use of that. You can measure it, but it's much lower than you would expect. And it's in particular difficult when people are not aware that the analogy exists. That means you try to solve the problem without being told, for instance, that it's the same thing. Or the other way, when it's a checkerboard, I would tell you, think of the wedding problem, the matchmaker, to help you solve that problem. That would make people aware about the analogy. If the problems don't share surface similarities, and surface similarities are something like that it puts in the same context. You may have a matchmaker in weddings, and then you may have some other matching two people for sports teams or something like that. Then you are quite similar in your description. But when you think about fields on a checkerboard and matchmaking, there is not very much surface similarity. And if these surface similarities lack and the problems only have the same deep structure, like in the example we had. And also time isn't helping. So if the solving of one problem is already a while back, then we find it more difficult and challenging to solve the current problem. And research has shown that people differ quite a bit in terms of inter-individual differences, how well they are using these type of analogies. Okay, let's summarize the theories of problem solving. We spoke in the very beginning about behaviorism, which is basically the trial and error approach, and usually for animals and small children it's learning by reinforcement. Then we spoke about Gestalt Psychology, where the Gestalt Psychology assumes that the whole is different from the sum of its parts, and it introduced the concept of the representation of the problem and insight, or aha, or illumination. This then led to the formulation of the Representational Change Theory, which tries to explain the processes involved in having those insights. And we have seen that it's changing the representation and constrained relaxation. Then in this video we spoke about the information processing approach, which is mainly for non-insight problems and can be considered to be rather formal, with start, state, goal state, and this well-defined problem space. And just a few minutes ago we spoke about analogical problem solving, which looks at how good are we at transferring previous solutions to new problems. Okay, if you have questions, post them on BBL. And this was everything for problem solving. In the last part, we will now speak about expertise.